Hi, everybody, and welcome to today's edition of the Spectral Geometry in the Clouds seminar. So this week we have the second part of two of a subject started last week by Daniel Stern. So this week we have Peter McGrath will talk to us about new minimal surfaces via equivariant eigenvalue optimization. Peter, the floor is yours.
Okay, thanks very much. So thanks for the invitation and also for allowing us to give two talks here. So I will assume most folks here saw last week's talk, or at least will look at last week's talk later if they haven't. So I won't rehash everything Daniel did last week, but I'll say up front, Daniel focused more on some of the analytic aspects of our construction. And today I'll focus a little bit more on some of the geometric aspects, sort of what some of these surfaces look like more, and their, the geometry and topology of the constructions. So let me start by talking about a very general definition for what are called surface doublings. So the setting is that you have three pieces of data. You have an ambient Riemannian manifold, which in this slide will be called N, a two-dimensional surface in N, which at the moment I assume to be embedded, and another two-dimensional surface called M. And we call M a doubling of sigma if the following conditions are satisfied. So first, the nearest point projection in the ambient space from M to sigma is at least well defined on M. And then the projection of M to this base sigma splits into sort of two pieces that I call sigma 1 and sigma 2. Sigma 1 is sort of a small piece. It's points and curves. And sigma 2 is a two-dimensional piece. And these two pieces, sigma 1 and sigma 2, are sort of characterized by the following properties. If you restrict to sigma 1, the pi or the pi inverse really is a diffeomorphism. And if you restrict to the sigma 2, you get a two-sheeted covering map, or at least the inverse image. Sigma 2 is a two-sheeted covering map. So this condition 4 is the genesis of the terminology doubling, because most of the this pi map is a two-sheeted covering map. So in this talk, we're interested only in minimal doublings. So we call such a setup minimal if both M and sigma, the base surface, are minimal surfaces. And in this talk, I'll call the doubling symmetric if there's an ambient isometry that fixes the sigma and sort of exchanges. Okay, so there are lots of minimal doublings that we know of. So in the next several slides, I give some examples, so starting with the very, very simplest ones. But one more definition on this slide. So the components of the sigma minus the projection, these are called doubling holes. And this sort of notion should become clear through the examples. So the first example is the catenoid in R3. So this is a doubling of the plane x3 equals 0. In this case, the way I've normalized things in this picture, there's one doubling hole. So the doubling hole is this disk in R2 that the waist of the catenoid sort of surrounds. And then because we can scale the minimal surfaces in R3, if we like, we can blow down the catenoid, and then we get a plane covered twice in the limit. Okay, so that's maybe the very, very simplest example of a minimal doubling. There's another completely classical example that's a little bit more geometrically interesting, maybe. And this is the singly periodic Shirk surface. So we can consider this a doubling as well, as if we like, also of the, let's say, x3 equals 0 plane, the z equals 0 plane, again in this figure. So there's the reflection that exchanges x, y, z and x, y minus z cuts this surface in half. And then there are these circles here, topological circles here, that are fixed pointwise on the Shirk surface. In this case, those circles, bound again domains on the R2, and those are all doubling holes, and the direction of periodicity is where my cursor is pointing here. So on this slide in this picture, there's just a couple doubling holes, but of course the surface extends infinitely in both directions. This case, again, if you take the blowdown limit, you get a pair of planes meeting orthogonally. And so just as a side note, the Shirk surface, again, can be considered separately from a doubling. It can be considered a desingularization because of this last point here. So if you look from very far away, you don't see the topology, you just see the asymptotic planes that appear to meet orthogonally. So I want to go to a slightly different flavor of example. So we can talk about non-orientable doublings if we like, and there's a very simple one that's sort of the analog of the catenoid, and that's this complete Mobius band in R4. So we can think of the Mobius band as this cylinder with this identification on the coordinate space, and then we have a very explicit minimal immersion here with these hyperbolic trig functions, and then the trig functions on the theta directions. And you can consider this as a doubling. If you write your coordinates in C2 like this, you can write it as a doubling of this z equals 0 plane. So it's what you can see from this parameterization is that the second two coordinates, or the second coordinate in C2, is roughly sort of at infinity. It's like the first coordinate squared. So you could think of this as asymptotically being like z equals plus or minus square root of w, and sort of at infinity, those are the two sort of sheets. And there's one doubling hole, the boundary of which is given by the curve, I think t equals 0 in this parameterization. And again, the blowdown limit is twice this two-plane in R4. So now I'd like to transition to some more sort of newer examples of doublings in the round three-sphere. And so this family of Lawson surfaces, the CG1 surfaces that Lawson constructed in 1970, these can be considered doublings of an equatorial two-sphere in S3. So here G in Lawson's notation on this slide is representing the genus. And these can be considered doublings with G+1 doubling holes. And the limit as G goes to infinity, there's a nice Farafold limit, and sort of in analogy to the Shirk surface example, the limit as the genus goes to infinity is a pair of these equators that meet orthogonally along a singular curve of intersection. So again, just like the Shirk surface, this family of examples could be considered desingularizations as well as doublings. I am not going to be talking about desingularizations at all for the remainder of the talk, but I just want to mention both of those notions, which are in general different, but some surfaces satisfy both. Okay, so at some point in the mid-80s, a discrete family, finitely many doublings of the equator S2 and S3 were constructed by Karpukhin and Stirling using a variant of Lawson's plateau method of construction. But the ansatz is very different for these. So the ansatz for these is that you begin with a two-sphere, and then you tessellate the two-sphere by polygons, regular polygons. And so there's a finite number of ways to do this using the Platonic solids. So here I have fundamental cells that are pentagons. And then what one can do is basically choose to put doubling holes on the centers or the vertices of this tessellation of S2. And so they construct 9 or 7, I think there's 7 maybe up to symmetry examples. So that have like dodecahedral or icosahedral or cubical or tetrahedral or octahedral symmetry. So there's this discrete family like that. And there are much more recently, there have been lots of very, very interesting constructions of doublings of minimal surfaces in S3, primarily of the Clifford torus, and more doublings of the equatorial two-sphere in S3. And these were sort of designed and carried out by Capelleus and some of his collaborators, including myself. So the first of these, the construction was completed in about 2010. And these were an infinite discrete family of doublings of the Clifford torus. And the family, at least in the original construction, is parameterized by a large integer n. And roughly speaking, what one does is takes the Clifford torus, which intrinsically is a square, and cuts the square torus into basically m by m subsquares by an m by n square lattice, and then decides to put doubling holes centered at the centers of those m squared squares. And for large m, one can construct a minimal doubling of the Clifford torus like this. The doubling is actually not symmetric because there does not exist a good isometry that fixes the Clifford torus, isometry of S3 that fixes the Clifford torus pointwise, unlike the prior examples I discussed. But for large M, the surfaces are nearly explicit. They're basically small perturbations in the vicinity of the doubling holes, small catenoids whose sizes are predicted or determined by the construction. So roughly speaking, the size of the catenoidal bridges, where by size I mean the, let's say, radius of the waist of the catenoids, is like e to the minus genus multiplied or divided by a constant. And then away from the doubling holes, the sort of the two-sheeting covered map, the two sheets look like just small perturbations, parallel copies of the Clifford torus. And so again, one can take the varifold limit as the parameter m goes to infinity and recover twice the Clifford torus in the singular varifold limit. So subsequently, David Weigel generalized this construction quite a bit for many more doublings of the Clifford torus, and even what he calls stackings, where the varifold limit is more than two copies, like say k copies of the Clifford torus for any integer k. I should mention one thing. So at some point in the 80s, some doublings like this, doublings of the Clifford torus, were proposed in this announcement by Pitts and Rubenstein. And their constructions were never fully carried out by then, but Dan Kiedover more recently has completed some of their constructions using the min-max approach. So Capelleus also constructed, and later I constructed many more examples with him of doublings of the two-sphere, infinitely many doublings and different families indexed by two discrete parameters. And the symmetries here are based or centered around sort of a dihedral symmetry, unlike the prior examples where one just had the Platonic symmetry groups. So you have a m-fold dihedral symmetry, m going around like this, and then an extra Z2 action telling you that what happens sort of above the equator is the same as what happens below. And in this picture, I have kind of a perhaps confusing looking stereographic projection of one of these kinds of surfaces. So you're sort of seeing the sort of outside and quote unquote inside in this projection of the doubling. Of course, because it's symmetric, sort of the outside and the inside are isometric. And again, the size of the bridges is like e to the minus gamma here, where gamma is the genus. And in the construction here, one allows sort of k different sort of rings of m necks each to be placed at certain latitudes here. So what would I like to tell you about in relation to the work that we've done with Misha Karpukhin, Rob Kusner, and Daniel Stern? So we have a very general theorem, at least first in the closed case, about doublings of the equatorial two-sphere. And so what we do is we begin with just a closed orientable surface, and we assume that it has abstract surface without even a Riemannian metric to begin, and we just assume it has a group action gamma of this form that I call reflection group here. So I didn't put the definition here. So here, reflection group just means that it's a group generated by elements that are called reflections here. And for the purposes of the definition, reflection means that it's an involution, and the fixed point set of the involution separates the M. So what you might think reflection should mean. So we have a group like that acting, and the only assumption we have is that the quotient by the Z2 factor in the group has genus 0. So if that's the case, then one can find a Riemannian metric, a gamma invariant Riemannian metric, and furthermore, an isometric minimal embedding into S3 such that the M viewed as living in S3, now embedded in S3, is actually a gamma equivariant symmetric minimal doubling of the S2, which has, moreover, one or two more properties. And one of these properties is that the area is strictly less than 8 pi, 8 pi being twice the area of the base 2-sphere that this doubles. So somehow that having these doubling holes only decreases the area. Okay, and as you might imagine, if you begin to think about these assumptions and what they allow, they're quite general. There are lots and lots of these surfaces that are, at least at the level of equivariant homeomorphism, clearly different, so that they give rise to non-isometric different minimal surfaces. So in particular, by doing basically the simplest non-trivial case where G is just the Z2, and counting the number, estimating the number of definitely different examples, one gets this linear lower bound on the number of distinct such minimal embeddings with any given genus gamma. So one gets lots of new minimal surfaces in S3. And I'd like to comment briefly in this slide about which groups G are amenable in this construction to be reflection groups. So it's actually very easy to classify what reflection group means in this context. So the reflection groups, the G in that example, are exactly basically the reflection subgroups of O3, which are completely classified. Obviously, these are the groups of the symmetries of the Platonic solids, the dihedral groups, and the sort of dihedral groups with the extra Z2 factor, Z2 itself, and then the trivial group. Okay, so all we need in this construction basically is to, basically the way you think about it, and I'll talk about this more on the next slide, is you take basically the 2-sphere, you put one of these O3 groups on the 2-sphere, and then you cut out holes in a G-symmetric way. You cut out holes, and those will be your doubling holes up to sort of homeomorphism. And then you topologically double that surface along its boundary, and then you get an M that has this group action on it. And then the theorem says that you get a minimal doubling with that discrete symmetry group. So it's quite general, and I want to discuss examples a little bit more. So here I've just drawn, again, a stereographic projection, a cartoon picture of one of these Karpukhin-Stirling surfaces. So I want to describe how it fits into the setting I just described. So here, if we imagine this picture as being basically just a decoration of a 2-sphere and these just being holes. So imagine this as just a domain on the 2-sphere, which I can think of as the quotient. I can think of as the M mod Z2, if I like. And then one can see this icosahedral or dodecahedral symmetry group acting on it, for which a fundamental domain is, for example, this triangle that I'm tracing out with my cursor here. And in this picture, there's just one doubling hole sort of sitting on one corner of one of the triangles in this fundamental domain. So what our theorem says in the context of the group that's already implicit in this picture is that on this fundamental triangle, one could put independently and arbitrarily any number of doubling holes along the vertices of the triangle. In this picture, there's just one on this one vertex. So you can put doubling holes on this vertex, this vertex, this vertex, as many doubling holes as you like on this edge of the triangle, as many as you like on this edge of the triangle, as many as you like on this edge of the triangle, and then as many as you like on the interior. Those are all sort of different choices up to equivariant homeomorphism. And then for any of those ways to describe the quotient, one gets a minimal doubling, and then one can do this for any of the groups here. So it's quite a flexible construction. So here I have another picture, cartoon picture, which tries to articulate the same thing I just described. So here I have a picture that's sort of 1/4 of a surface M with I think a dihedral cross Z2 symmetry group. So 1/4 of the surface is pictured here, but this 1/4 of the surface already has 6 fundamental domains, 1, 2, 3, 4, 5, 6. And so if we look at one of the fundamental domains, which is a triangle, in this picture, I've cut out 3 doubling holes along this edge, 1 along this corner, none along this corner or here, and then just 1 along the interior of this face. And as I mentioned before, the construction allows you to make all those choices, how many you have along this edge, this, along the interior of the face, or along the vertices. They're completely arbitrary and independent choices. Okay, so that's basically the topological level on which our construction works. And I'd like to maybe connect this with the story Daniel was telling last week about the eigenvalue optimization, and at least describe some of how we get the geometric conclusions, some of which he alluded to last time. So maybe to very, very briefly recall some of what Daniel discussed. If one looks at this quantity here, so one fixes a closed surface and a group action that are called gamma here by a fixed group, say one looks at the normalized eigenvalue with respect to a particular gamma invariant Riemannian metric, and then takes the sup of that over all such metrics. If that sup is achieved by a smooth metric, or smooth except for finitely many singularities, then one gets a branched minimal immersion by first eigenfunctions. So for the rest of this talk, I take that as a black box. And for most of the rest of the talk, I won't even discuss any of the subtleties about whether this sup can be achieved. So Daniel spent quite a bit of time discussing what we know about that and what we don't know about that. But I'll just recap some of the main challenges about trying to construct minimal surfaces in this way. Obviously, as Daniel pointed out, in general, it's not known whether this supreme normalized eigenvalue is actually achieved. And we have shown in many cases with many group actions it is, and that's what I'm telling you more about today. But beyond just the existence, if one is trying to construct nice embedded minimal surfaces, there are 2 other main challenges. One of which is that controlling the codimension, the dimension of the first eigenspace, is in general a problem, because in general one expects the dimension of the first eigenspace to actually grow linearly with the genus of the manifold. And furthermore, it's possible that one doesn't actually get nice embeddings. One could truly get immersions or branched immersions. And so there are examples that demonstrate, simple examples that demonstrate that both of these things actually happen, even when one can prove that the supremal eigenvalue is actually achieved. So for the rest of the talk, I'd like to discuss a little bit more of the geometry of some of the surfaces we construct, and then maybe discuss a little bit how 2 and 3 get resolved. So to this end, I want to tell you in a little bit more detail about some of the symmetry assumptions that we assert for many, but not necessarily all of our constructions. And so I want to give an actual definition of what I mean by a Riemannian reflection. So if you're listening carefully, the definition I'm about to give you now is slightly different than what I gave on an earlier slide. And I may comment about that later. So here we say that a reflection is just an isometry such that there exists a fixed point such that at the linear level, the differential is a reflection in the tangent space. So the tangent space of this fixed point, it's a Euclidean vector space. And then we request that the differential is actually a reflection about a line, let's say when we're on a two-dimensional surface. So you just need to find some point that's fixed by the involution. And then at the linear level, you look like a reflection about a line. And so completely standard theory tells us that the fixed point set is a disjoint union of totally geodesic components. So that means embedded curves and possibly isolated points. And the nomenclature that's often used is that the embedded curves, at least when they're closed curves, if we have no boundary, for example, they're called ovals classically. If we do have boundary, there's some notation that will be convenient later. So you can have these fixed point components, the curves that actually do meet the boundary, and I call M super rho sub partial sub boundary just the union of all these components. And so now I come to a definition. So this is a definition of some class of surfaces that have some mild symmetry, and this is the sort of the least we need to get nice geometric conclusions for surfaces with some symmetry groups. So we call this class of surfaces basic reflection surfaces, and a surface M with a reflection that I call tau here, we call it a basic reflection if we just have these simple two properties. So first is just that the quotient by the order 2 element just has genus 0. And the second, which is vacuous if we're a closed surface, so it only matters if we have boundary, is a little bit more technical, but it's that if we take the union of the boundary and this all the fixed point curves that meet the boundary, if we take the union of that and look at its image in the quotient, that's connected. Okay, so for the next couple of slides, I'd like to tell you a bit more about basic reflection surfaces, this simple class of surfaces with symmetry. And so a very simple observation to begin with is simply that each topological type, and we can have different worlds in which we sit, but in each case, each topological type, whether we're considering orientable, non-orientable, surfaces with boundary, surfaces without boundary, in either case, each topological type is realized as a basic reflection surface. So this is not very difficult to see, and I just want to outline this in the simplest case. So in fact, it's not very difficult to classify up to equivariant homeomorphism, just up to the Z2, what all the basic reflection surfaces are. So in the closed orientable case, it's very simple. It's sort of exactly what you think, or the simplest example you can imagine in your head. You just take a genus 0 surface, cut out, so take a sphere and cut out a certain number of disks, and then that's a genus 0 surface, and then double that surface along its boundary. So after you've doubled the surface along its boundary, you've gotten a closed surface now with some genus, and then because you've doubled along the boundary, you have a reflection. And by construction, that surface is a basic reflection surface, and by varying the number of holes you cut out, you can make the genus arbitrary. And it turns out that up to equivariant homeomorphism, every closed orientable surface that has this basic reflection surface property arises in this way. Okay, and so I've tried to articulate a couple of the fixed point ovals here that go around like this and have these dotted backsides, and then tried to articulate some of the topology there. So if you wanted to turn one of these closed basic reflection surfaces into a basic reflection surface with boundary, at least up to equivariant homeomorphism, you could just cut out a number of disks that meet one of these single ovals, fixed point curves on the surface, and then you would get a basic reflection surface that's orientable with boundary, and then has any prescribed number of boundary components. And so if you just cut out all of the circles along one fixed point circle here, you'll clearly satisfy that second property there. For the non-orientable case, I just want to describe briefly how one can get lots of non-orientable basic reflection surface, at least in the closed case. In fact, what I'll describe here is the way to get all of them up to equivariant homeomorphism. So what one does is one takes a genus G surface for any G, including 0, and then starts with an involution on that surface, not a reflection to begin with, that fixes 2G plus 2 points here. So like this point here, 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 and so on and so forth. This example. And then, so that surface with that involution is not even a reflection surface, but what one can do is, and it's orientable to begin with, but one can do is in a neighborhood of any of these isolated fixed points, one can cut out a disk containing the isolated fixed point and replace it with a cross cap by just identifying the boundary of that circle with itself via a local antipodal map. And then one's gluing in a cross cap. Independently or alternatively, one could also cut out a pair of disks along a neighborhood and then its image under the involution here, and then identify those two boundary circles with each other, or alternatively glue on a cylinder connecting those two. And that also makes the surface non-orientable. The first thing I described, adding a cross cap about an isolated fixed point here, makes the surface non-orientable and adds 1 to the non-orientable genus. Adding a handle like I mentioned there, adds 2 to the non-orientable genus, and then turns doing any one of those operations, or doing those operations any number of times, keeps the surface a non-orientable basic reflection surface. It's not difficult to check. And furthermore, one can check that all of the non-orientable basic reflection surfaces arise in this way that I just described, at least in the closed case. And then a similar modification takes care of the boundary case. But I'd like to mention maybe now why we care about the basic reflection surfaces, why they're helpful for the constructions that we do. So there are a couple different reasons. The first one I already articulated, they're at least a flexible, simple class of objects that realizes every topological type. But a more geometric reason is that there are simple a priori bounds, upper bounds on the first normalized eigenvalue, independent of the topology, completely independent of the genus or number of boundary components. So for any BRS, in the closed case, so we use M for the closed case, N for the case with boundary usually. The first normalized eigenvalue is always less than, so I've made a mistake here. This should be 16 pi here instead of 8 pi. It's easy to get mixed up between whether you're thinking about area, if you're thinking about a minimal surface, or the actual normalized eigenvalue, because there should be an extra 2 here. So this should be 16 pi here. In the case with boundary, you get 2 pi. And so in particular, if you could solve the eigenvalue optimization problem, and we do, the branched minimal immersions that one would get are always embeddings automatically by sort of Li-Yao type results. So Li-Yao in their early 1980s paper proved that a branched minimal immersion of the closed surface into an n-sphere is an embedding so long as the area is less than 8 pi. And so all these examples would achieve that threshold, and completely analogously in the case with boundary. So when one is below the 2 pi threshold, again, 2 pi being the area of 2 disks, 8 pi being the area of 2 spheres. So these surfaces would have to be embeddings. That would automatically remove one of those difficulties. So there are no branch points, and then the immersions actually must be embeddings. So on a slightly different point of view, one can also prove that the dimension of the first eigenspace, as long as one has a metric, Riemannian metric, that respects the group symmetry, the dimension of the first eigenspace is always as small as possible. So, for example, in the orientable case, in the closed case, the dimension is less than or equal to 4. So if you had an embedding by first eigenfunctions, it would go to the 3 sphere. And in the case with boundary, the dimension is less than or equal to 3. So one would get an embedding into the 3 ball. So the conclusion is that, again, sort of for free from this result, one would always get codimension 1 embeddings. Okay, so I'd like to connect back to these results also with the talk about doublings I gave earlier. So I'd like to state kind of a long and technical theorem that summarizes the results on the previous slide and also goes a little bit further and says that the minimal surfaces that we construct in the closed case from the theorem I stated earlier, the ones that I said were all doublings, I want to connect with that here. So this is a kind of technical theorem from our paper, but it says a lot, so I think it's worth writing it down. So if one has a branched minimal immersion of a basic reflection surface by first eigenfunctions, then one has a lot of nice things. So first, the dimension is 3 if the surface is orientable. Second, that this tau, the reflection, the intrinsic reflection, is arising from reflection through a 3-dimensional subspace of the ambient Rn. So the intrinsic reflection truly is coming from a reflection through a totally geodesic 2-sphere in the S3 if we're orientable. Furthermore, each oval, the fixed point circles, they're convex and in particular embedded. So those are the boundaries of the doubling holes. And in particular, the next item is that the minimal surface is actually a doubling, symmetric minimal doubling of the equatorial 2-sphere, the equator being this plane P that I talked about earlier. And lastly, the area is less than 8 pi. So this conclusion 5 is re-articulating what I said on the previous slide about the eigenvalue bound being less than 16 pi, given that the eigenfunctions have eigenvalue 2 in this case. And let's see, what else? This embeddedness is coming from that Li-Yao bound. But more strongly, we have much more than just embedded. We have this doubling property. So we have actually a lot of structure. So away from these doubling holes, the minimal surface is actually a 2-sheeted graph over a domain in the base 2-sphere. Okay, and furthermore, if the minimal surface itself had a further group action, so if we had beyond just the Z2 factor, if we added some additional symmetry, as we can in many cases and our theorem allows, then the embedding itself is symmetric in sort of the natural way, as one expects. Okay, so in some of the remaining time, I'd like to talk just a little bit about how some of the proofs of some of these parts go, and then discuss a little bit about the case with boundary. So for the most part, the proof of this result is quite elementary once one has all the definitions right. So I want to just briefly discuss through how one of the results goes. So for example, this bound on the dimension of the first eigenspace for an orientable closed basic reflection surface. So I want to sketch how that goes. So first you can split the eigenspace into the sort of even here and odd parts under the involution tau, and you consider them separately because you have this direct sum decomposition. So the odd part is very easy. So you have all these fixed point circles that cut the surface into half into genus 0 pieces. And so in particular, the fixed point circles, they separate the manifold. And if you have an odd eigenfunction, you vanish on all these fixed point circles. And so in particular, you have just two nodal domains by the Courant nodal domain theorem. And so the two components, after you cut out the fixed point set, they are the nodal domains for any odd eigenfunction. And that means that the space of odd eigenfunctions is at most one-dimensional. So this factor here is at most one-dimensional. So then in the next slide, we analyze this factor here, which we show is at most three-dimensional. And so for this, I'm going to put a cartoon figure on the right side. So I put the cartoon figure here. So I kind of reused a figure I had from before. I'm viewing this figure in a different way. So think of this figure as a genus zero surface. So I've cut out a number of disks from a sphere, I guess, including sort of a large disk, depending on how you think of it. So one can think of this either as the quotient of m by the z2 factor or as just half the surface. They're the same in the orientable case. And if you have an even eigenfunction, then it satisfies a Neumann condition on all of these circles. And then you can consider the nodal set. And the advantage of being even is that when you're seeing half of the surface, you're seeing basically all of the relevant information, because on the other half, it looks the same because it's even. Oops, it's gone too fast. So it's not hard to see that the nodal set sort of meets each of these fixed point circles, either zero or twice up to multiplicity. And then furthermore, if you fix a point P that's not on these fixed point circles, it's not hard to see that the differential there can't vanish if you have a point in the nodal set also. So you can't have a cross. You can't have an interior cross not on these fixed point circles. And again, each of these facts comes sort of very quickly from the Courant nodal domain theorem that any even U first eigenfunction like this just has to have just two nodal domains. And so then it follows that the even part of the first eigenspace has to have dimension at most three. So I'd like to make quickly a couple comments about the non-orientable case. So many of the conclusions in this technical slide about the properties of minimal immersions of basic reflection surfaces hold for the non-orientable surfaces. So the only time in this slide that we talk about orientable surfaces is here. So most of those conclusions hold if one has a minimal immersion of a non-orientable basic reflection surface. But of course, the dimension bound would have to be different because, for example, by Alexander duality, you can't even embed a non-orientable closed surface in S3. So you would need at least to go to S4. And so we can prove and do prove optimal dimension bounds or multiplicity bounds for at least a subclass of the basic reflection surfaces that does realize every non-orientable topological type. And if we do have such a surface, then we can prove that in essentially the same way. The details are just slightly more complicated, that we would get the optimal dimension bound of 5 rather than 4. So if we had minimal immersions of such surfaces, they would end up in the 4 sphere as doublings of a 2 sphere. What about the case with boundary? So the case with boundary, the story is very much analogous. We have just this extra condition. So there was that second condition, the definition that I recall here quickly. So the second condition was that if we take a look at all of the fixed point arcs that meet the boundary and we take them with the boundary, that set is connected in the quotient. So what that means geometrically or topologically is just that the quotient is just a disk with a number of holes removed. And that's the right assumption to get a lot of the analogs of the preceding results to go through just in the setting with boundary. So many of the proofs work in the same way or very much an analogous way, with the obvious differences on the dimension bounds and so on and so forth. So that's what allows us to get the embeddedness, the area bounds, and we do get that the analogous property about doublings. So we would get that the corresponding immersions are embeddings and they're doublings of free boundary doublings of a two disk. But the proof of this last part that one gets doublings is a little bit more, or maybe quite a bit more involved. Instead of just using the Courant nodal domain theorem, one has to use somewhat more elaborate sort of Morse theoretic results. So there was a fairly recent paper of Brian White and some collaborators where they set up a kind of Morse theory, or they call it Morse-Rado theory on minimal surfaces. So we use some of that technology to prove we get doubling. So I state the analogous theorem. So I'll go through it a little bit quickly. It's the very much analogous to the theorem I stated before, but we're just in the boundary case. So we start out with the surface. I should have put ends here everywhere because we're supposed to be using ends for surfaces with boundary. So if we have a branch middle immersion of a basic reflection surface by first eigenfunctions, then we go into the three ball if the surface is orientable, and the reflection is coming from the reflection in a two-dimensional plane. And then the fixed point ovals are convex curves. And then we can say something about the boundary, sort of the boundary piece. It projects at least on the plane to a nice curve, the circle. And then we get a doubling of the disk with area less than 2 pi. So that's maybe the sort of geometric conclusions we have. And I just want to state now maybe the main theorems from our paper about the existence of minimal doublings like this. So maybe before that, here's a nice picture from Mario Schultz's website of a rendering of a free boundary minimal surface in the three ball. That's a doubling of the disk with genus 3 here, and then one boundary component. Okay, so one of our main theorems in the setting with boundaries says that we do realize every topological type of surface, in particular, as a symmetric doubling of the disk with area less than 2 pi. And we get lots of them again. So if we consider the genus, the number of distinct ones we get, at least with this, that should be a Z2 there. With this Z2 cross Z2 symmetry, grows linearly with the genus again. We have also results that are not for basic reflection surfaces. So in particular, in the genus 0 case, we have lots of constructions of minimal surfaces that are not necessarily basic reflection surfaces. So I just enumerate one of the results we have there. So we get lots of genus 0 free boundary minimal surfaces there with area less than 4 pi. And we can assert lots of symmetry groups. Unfortunately, at the moment, we don't have as complete a theorem as we do in the closed case. So we have to say something like there's a large class of reflection groups. And then in the paper, we have kind of a technical and exhaustive list of which ones we can prove the existence for at the moment. So I think I stop here. Yeah, thank you for your time.
Thank you very much for your talk. We have time for questions. If you have questions, please unmute yourself or ask them in the chat.
I think also I have when you're looking at higher genus than 0, the number of boundary components stops entering into this lower bound. Do you still expect the number of boundary components to push up the number of
this number here, this count here?
Yeah.
Yes. Yeah. So the count here, we don't expect to be sharp or anything like that. The count is just based on in the sort of simple setting where we can do this Z2 cross Z2, which is sort of one of the settings. But it's sort of simple because it's very flexible. It's just sort of easy to enumerate ones that have to be different up to the sort of equivariant homeomorphism level. So yeah, so we don't expect these enumerations, these counts here to be sharp in any reasonable sense.
Anyone else wants to ask something or comment on something?
For the case B is 1 and gamma is 0 case, can you construct free boundary minimal surface in your method?
So gamma equals there's a genus 0 and 1 boundary component.
Yes.
In other words, the disk.
Sorry. B is 1 and gamma is 1.
1 boundary component and genus 1.
Yes.
Yes, we do get such an example. Yeah.
Oh.
I have a very naive question also. Like the surfaces that you get are distinct from those obtained by various other methods, right?
Some of them are. Some of them we definitely expect to coincide with surfaces obtained by various other methods. So.
And is it possible? Do you have proofs of some of these correspondence?
No.
I mean, other than disks and things like this.
I mean, yes. I think in the paper we don't prove that any of the surfaces that we construct must be the same. I think maybe for some cases, possibly with further work, we might be able to do that. But there are certainly many of the symmetry groups or actions where we do expect the surfaces to line up with other constructions. So there's just lots of constructions. So for example, there's I mean, many so there's genus 0 doublings of the disk by Fulha, Picard, and Zolotareva that and then there are genus 0 not doublings but genus 0 surfaces constructed by Capelleus and Zhu that sort of look like desingularizations of various catenoids and disks that go at the boundary. Some of our dihedrally symmetric genus 0 examples I would definitely expect them to coincide with those examples.
So is there a sense that for a fixed genus in number of boundary components, or for a fixed genus in the closed case, that there is a kind of space of these surfaces that one could understand? Or
I mean, to some extent, one way I like to think of some of what we've done is to explore that space, in the sense that, at least like going back to the main theorem I stated in the closed case, which is at least maybe a simpler regime. So of course, a major open question is whether there are continuous families of embedded minimal surfaces. So we obviously don't go anywhere towards answering that question, but at least in understanding maybe in a much more specific regime, you could try to ask more about the space of doublings of the two-sphere in S3. In general, I think this is sort of a hopeless task because there are just so many configurations one might ask about. But this theorem that we've stated here does tell you that many configurations of doubling holes that you expect to give rise to a doubling do, in fact. And so and that some of that is new, especially for low genus examples, and the examples with lots of the Platonic symmetry, there weren't constructions that gave those doublings before. Of course, with Capelleus, the work I did with him earlier, we did a huge collection of dihedrally symmetric doublings. That's much more general than actually this theorem states here, what we have proven. But one virtue of this theorem is it says, in some general sense, that if you have sort of a configuration of doubling holes with some symmetry, and you say, does this give rise to a doubling of S2 and S3? This theorem basically says yes. So lots of things that you expect to look like doublings do. And at least this was definitely open. Like if you imagine these kind of Karpukhin-Stirling examples, you can do lots of decorations of a two-sphere and put holes in lots of places. And their original construction just allows you to do the very, very simplest possible situation where you just have one hole on a single vertex. So I don't, that's maybe a specific answer to a question that's more general.
Well, it's mostly a naive question, but thank you.
I have a question.
Yes, Mamadou, go ahead.
Thank you. In some sense, we use minimal surfaces like surface where the mean curvature is equal to 0. Here, the minimal surface is like measure is minimal. What about minimal surface like mean curvature is equal to 0?
Let's see. Sorry, could you say that again?
Minimal surface is like the surface when the measure is minimal. And sometimes we take minimal surface has a surface whose mean curvature is equal to 0.
Yeah. So all of the
I want to say if we have a link about surface where mean curvature is equal to 0.
So all of the surfaces here, the mean curvature is 0, and most of these surfaces are not. I mean, for minimal surfaces in the sphere, they're basically always unstable, so they're not like area minimizing. So maybe if I may not understand your question, but all of these surfaces have mean curvature 0 everywhere.
Okay. Sometime in study we look minimal surface has a surface where the mean curvature is equal to 0. And here you make the study has a surface have a minimal area. Is it?
So we don't actually, yeah. So in this discussion, we're not assuming that the surfaces have minimal area. We're actually the starting point is that they have a mean curvature 0. So they don't.
Okay.
They're not necessarily absolutely area minimizing.
Okay, there's nothing. Thank you.
Thank you. Anyone else before we go? If not, let's thank our speaker again. And we will reconvene next week with a talk by Alessio Figali, who will speak about free boundary regularity for the obstacle problem. Until then, I wish you a very great week, a good week. Thank you.
Thanks a lot.
And thank you, Peter.
Thank you. Yeah, thank you for hosting.